because of the time. So again, Ophir, thank you so much, and please have a look at the Q&A, so you'll be able to answer the questions. All right, so our next speaker is Nadav Mazor from Vayar, and lead RFIC design, working on radar applications. So please, without further ado, go ahead. Yeah.
Thank you, Vadim, and thank you for this session, interesting sessions. So following Jürgen and Ophir's sessions, I have some things here which will continue, I guess, some of their topics in their talks. So I'm gonna talk about motorcycle riding and the advances in RFIC which make it safer. So the outline of the talk, a bit about the company with respect to general applications in automotive, some insights on ARAS, which is Advanced Rider Assistance System, enablers for ARAS radars, and their challenges, and then some insights on facing these challenges. Some of these challenges were mentioned in the previous talks. I'll touch performance verification while I'll succeed in the amount of time and summarize. So just to you all, I mean, maybe less familiar with Vayar. So we have 4 RFIC generations launched. Vayar was beginning its way with medical product for breast cancer detection. Later on, Wallabot, our handheld kind of pipe detection in wall and in depth wall, drywall for home DIY. We're in the robotics, smart building kind of applications, but mainly ADAS, ARAS, and senior care. So in the senior care, Vayar sensors are detecting falls of seniors in elderly care facilities in the US and around the world in several places. And the idea is to bring the caregiver as fast as possible to the senior which fell. And in the car, detecting a child which were left in the car, and motorcycle safety. So if I'm looking into the automotive parts of what Vayar is into, so in the in-cabin, in a single sensor, full cabin detection, which brings applications such as the presence of a child, seatbelt reminder, and one can use it as classification and work with a point cloud for other needs, such as airbag suppression and others. So this is quite a cool application, and I think the most value from it would be less and less child left in a car, in a heated car, to die. So that's kind of the intention of this application, and I hope it will start being a standard everywhere, and shortly it will. Today it's only safety points, but I hope later on it will be a must. In the out of car, I think in the previous slides of Ophir, it was discussed more thoroughly, but we also understand that a multi-sensor, which includes cameras and sensors, are the way forward with 360 degree surrounding. Having saying that, we still believe that the low-cost kind of multi-sensors are the approach, and low-cost is kind of what we're up to in a general state of mind. In the ARAS solutions, which is the motorcycle, bikes, applications such as, again, collision warnings, adaptive cruise controls, etc. ARAS requires slightly different requirements, and that's what I'm gonna try and show it here. Just one moment, I'm trying to move the bar here. Yep. Okay, so so what you see here on the right are a few motorcycles with VIAR's radars in front and rear. This is for, as I said, the applications discussed. Generally speaking, the ARAS application, one can think of a lane change assist and other maybe high beam control that could be added up. But this is a basic safety feature that we believe must be in motorcycles. And I think that the main challenge of having a radar in a motorcycle, other than that is different than the ADAS kind of comparable kind of to the cars, is the tilt. The motorcycle tilts to the right and to the left during the drive, during the ride, which challenges the ARENA classification, and then a higher resolution both on the angular and the horizontal or the azimuth is needed. So ARAS is available on premium bikes, and actually over there where money is not an issue, you can see these safety features saving lives. But most of the bikes around the world are practically very low-cost bikes. I saw on the internet some 5K even dollars or euros, but I understood that there are even lower-cost bikes. And these lower-cost bikes won't afford high-cost solution for safety. And that's where cost reduction is a must. The number of antennas, I think it was mentioned in the previous presentation as well. It's required. We want resolution rather than separability. We really want to detect the tilt angle and to be able to reject side lobes. So that feature is something that we're looking into. Field of view on the back, the requirement of the motorcycle industry is a wider field of view in the back to detect crossing cars, and in the front a bit narrower and further away. You can see examples of our rear and the front radar solutions, which show maybe doubling the field of view when you go to the back, and somewhat doubling the distance when you go to the front. And the resolution is a bit higher when you look at the front radar. Efficiency is always interesting, and I think maybe all of us should understand that when you're talking about efficiency, you're talking about cost. It's not only about DC consumption, battery, stuff like that. It's about heat dissipation, and it's about how you dissipate that heat. And dissipating the heat is a high cost thing, either with heat sinks, shield, backplates. So that's kind of high cost business. Other than that, the BOM that you have on your PCB gets higher cost, because the DC to DCs that deliver these amounts of DC costs more. So this way of thinking brings these four kind of main key enablers for densing in a multi-channel radar. So taking these 4 elements inside, Vayar sees the single chip solution as the main approach. In a single chip solution, we practically save a lot of money on layout area and a lot of DC consumption. And we talked about how efficiency is cost as well, while we're reducing the number of IOs, communication paths, number of LDOs, bias, band gaps, all those elements that are shared with all ports, system PLL, digital, processing, memory, etc. When you have them all together, if you can, of course, if you can't, you can't, but if you can dense them all together, you save money, you save heat, and you save DC consumption, and you have a very nice and clean solution when you're minimizing routing on the PCB. You get a very clean and nice solution. So this is our example, as I showed you in the previous slide, of the 76 to 81 gigahertz 22 on 23 module for front radar motorcycles. It includes the DSP, ARM, memory, and practically this is a full solution for the front. Now, if I'm looking at large number of antennas, one can argue that why large number? Let's go for smaller number, higher power with respect to EIRP, and maybe save some area on board on the PCB. So over here, you can see on the right, on the top, a power combining example, and on the left, the obvious kind of beam forming way of thinking if multiple transmitters are transmitting together. So from an SNR point of view, let's assume that we're similarizing the SNR. We have similar EIRP and we have same noise figure, because multiple receivers do not change the noise figure, and we can deliver, let's say, with same efficiency of PAs, either distributed to few PAs or single PA, and have similar SNR. But with respect to resolution and array design, the more transmitter and receiver channels you have flexibility on your array. You can define or have your array well sampled or sparse or any combination between them. But when you have a low channel count, you're practically sticking to either a sparse or a reduced performance, and then side lobes are more of your problem. With respect to resolution, I think it's obvious. With respect to dynamic range, again, the side lobes are one of the main obstacles for dynamic range when you have high side lobes. I like the modularity kind of thinking, even though sometimes harder to find applications really utilize this. But think of a single PCB which has wide field of view antennas that once you use it with aggregating the power to a beam and have it focused, and on a different application, not combine the power, and then have a wider field of view coverage, or use less antennas or less or few of the antennas for different applications. So you have one product, you pass it regulation, you create manufacturability on it, but it actually used for a few applications. And processing load, I think, Ophir, in your PPT, it was pretty clear that the data crunching is getting larger and larger, and yeah, and processing load is one of the main problems with multi-TX and RX. Other than processing load, we have issues of isolation. As Mobileye mentioned, the TX separated from RX for leakage purposes. So this is an issue and needs to be dealt with if you want everything clean and nicely handled together. Accurate modeling is not obvious because of the density of everything combined together. Heat, calibration, and even performance verification has to be a bit different when you have such a dense system. So I'm not sure I'm gonna, renew anything on anyone's head right now, but process nodes go to I don't know, higher end nodes costs more. If you want, you can look at the cost per wafer, which is interesting, and I think it's the most interesting parameter when you think of the cost per silicon in production. Now, like cell phones, when you buy the newest cell phone that is just now out of the market, it costs a lot. But when you buy the one that was just the last generation, which was just one generation back, you save sometimes even half of the money. And this kind of trend is seen here. You see how cost per wafer is practically saturated on around $3,000 and then rises up. This table is, of course, old. It's just a representative of how process nodes cost change throughout the nodes. And this is a snapshot in time. But one can think that, a few years from now, process node, which was like 40 nanometers or 28 nanometers in this table, will saturate to closer or set closer to the older process nodes. And why am I mentioning this? When we're talking about processing load and we're having high level of integration, we usually think of CMOS as the best choice. And then, as Jürgen said, that CMOS ate the SiGe. So we're in CMOS now, but now digital is kind of overcoming the RF, right? As Jürgen said in his presentation as well. So if digital is like kind of the big ticket item now, one needs to look into his solution and see if the digital doesn't exceed some 70–80% of the silicon area. If it does, one needs to consider moving forward to higher end process nodes. Of course, that brings some challenges on RF and leakages and stuff like that. But from cost perspective, that should be kind of the right move if your digital is overcoming the RF. Now, during the years, you shrink the digital by half. So that doesn't shrink the full silicon by half because it's only 80%, let's say, of the total solution. But if you jump to a process node which is double the price, within 2–3 years, it won't be double the price, and then you get kind of a better cost effective solution. Let's talk about isolation for a second. So our system is based on a 10 gigahertz kind of signal generation, 10 to 20, sorry, signal generation, modulated, multiplied by 4, and distributed. Now, when you look on a system like this, which is not a zero IF, or could be a zero IF, but in this situation, it's not a zero IF, you see more or less 4 types of isolation or leakage paths that can disturb the system. Let's start from the easiest one, the TX over RX. That limits the RX sensitivity. So what it does, it simply comes from the TX to the RX antennas, and it has something to do with the TX noise if the TX over RX is on different frequencies. And that can challenge the system if there's not a sufficient isolation. There's the TX to RX LO leak, which is mainly interesting when you're on a non-zero IF, of course. If you're a zero IF, this is not an issue. This is nothing. There's the subharmonic emissions, which are practically regulatory. You don't want to emit energy out of the mask. And there are these baseband spores, which actually are the day-to-day habit of RF designers, or RF, post-silicon maybe engineers, that struggle in the lab in order to understand where did this spore come from. They come from DC-DCs, they come from system PLLs, they come from everywhere. But these are these kind of spores that you want to make sure that you're avoiding. If I'm looking on the TX to RX, the distance between the antennas and and the shape of the antenna, or the type of the antenna, with its wide field of view, define this leak path. Now, if we want to have a wide field of view kind of applications, and our antennas in part of their in one of their dimension is wider, we want to avoid that this width will challenge the isolation as well. From the top part, if the signal is too high, it can exceed the maximum linear reception area, so compressing the A to D, for example. And on the other side, if the TX noise is too high, and these calculations has to be done in each system, what is the TX noise emitted to the air? If that TX noise after the 35, for example, in this example, dB of leak exceeds the effective noise floor, you're practically degrading your noise figure. So these both of these barriers have to be looked into when we're doing a very dense system. If I'm talking about architectures which are non-zero IF, if a TX leak in the distribution network over RXLO, practically what you see, you're starting to see the harmonics of the IF. These harmonics of the IF can disturb in detection later on when you're trying to distinguish between targets. So this again has to be looked into. Now, things like for rule of thumb from our experience, but of course, there are always techniques to slightly improve. But as rule of thumb, when you have two differential lines running in parallel along a long distance, you can assume some 70 dB of practical kind of isolation. But once you have an underpass, this already degrades to around 60 or 60 something. And really need to be careful about these underpass, how close they are and how good is the ground continuity when you're doing them. A bigger challenge is when you need to cross diagonally, or you need to cross in a way that is more complex. And these angles, like 45 degrees, are more challenging with respect to leakage. And then you can suddenly fall to around 45 dB of leak, and that's bad. But then you can put in techniques like twisting the pair of wires, and help out with that, and that may improve things by some 12 dB and bring you back to the order of magnitude of the underpass, which was orthogonal. But all these modeling of the intersections inside the distribution networks are key to reduce the TX over RXLO leak. Subharmonics. This is from a paper from Comcast 2019, but just as an example, a quadrupler usually has subharmonics, and mainly designers look at the direct path, how good do they reject harmonics, and what were the subharmonic emissions through the antenna. but I don't think that this is the main challenge. Usually multipliers have techniques for filtering out. For example, over here, the doubler amplification, then another doubler with bandpass filter inside. And we get some 28 dBc, for example, a second harmonic rejection, which is directly after the multiplier. But after that, you have a lot more cells to pass through, right? You have PAs, you have layer transfers, you have the antenna. So practically speaking, subharmonics or harmonics in the main pass are not necessarily your problem. Usually your problem is coming from the supply. What happens is that when you're doubling a signal, you have balloons, and when you're not keeping your signals completely differential, you're relying on the supply path being good enough as RF ground. In a practical case, it's even really hard to model how good is your supply path, or how good is your low ohmic supply path. For example, if you're having some of the capacitance on silicon, some of them outside the silicon, what would be the impedance modeled? These capacitors outside of the silicon, when you put for supply, usually are not modeled for 80 gigahertz or 40 gigahertz. And one needs to look into what kind of system does he have when he's trying to filter out these emissions through the supply. So this is kind of just for, you know, warning, kind of when you want to reject the signal that you're seeing through the capacitors of the supply. If you plan for a filtering, which is some, I don't know, 12 dB or more in a 50 ohm network, you can practically maybe achieve a filtering of 5 dB or 4 dB. So be aware, modeling of this supply network is not obvious, and then filtering is not obvious as well. So this is something that we would like to pay attention to in our design, either with an L-choke or other things, and really try not to degrade the VDS of the device. I mean, we don't want IR drops too much, but filtering this out is crucial for regulation. The other spores, they're coming from everywhere practically. So these spores can come from DC-DCs. There are DC-DCs that are tricky, that are changing their PWM frequencies during operation in order to be able to deliver more current or less current. And there are clocks, and usually you have in your system a system PLL, a crystal. You have maybe other communication elements if needed. I don't know if you're trying to, if you have a SerDes or other high-speed paths. Now, one of the things really need to understand in the floor planning of the silicon is where these sources of signals are located, and where are your baseband wires going to the A to D passing through. If they're passing under a supply pad, for example, and that supply pad is fed from a DC-DC, which is not sufficiently filtered, the way to reduce leakages could be, again, twists over the wires and having the wires nicely differential underneath. So this is a case where you practically go under the aggressor, but you're avoiding the leak by the twist. Now be careful, because sometimes when you go under a differential signal, these twists can either subtract or combine the energy. So be careful what you're practically doing with these twists. And of course, ground shielding and keeping things differentially are always good secrets, but need to pay attention to this. And this is rather challenging when you have a lot of channels to work with. With respect to modeling, one of the biggest kind of questions when you have a complex system is that you're searching for the 50 ohm kind of reference. You're searching for what is the shared point when I'm communicating with another designer. How would I EM this module? I mean, sometimes when you have multi-TXs, how much of them will be put together for one EM model? So one of the things we're doing in VIR is we're cutting in a clearer references, for example, inside the package or inside the PCB, where the 50 ohm is practically more clear. And then the layer transfer to the silicon is modeled with CST, and the EM model is inserted to cadence and is, from that moment, part of the PA design and part of the LNA design or the receiver design. So once that's done, all the performance is practically showing results on a 50 ohm wire inside the chip package. So this helps with communicating the performance and having a clear reference and designing the PA and LNA or direct mixer inputs. And when you're looking a bit inside the silicon, now when you add this model of the CST, let's say, with an ESD solution and the matching network to the PA, if you're cutting the elements in a way that is not let's say messing up your cadence schematic, you sometimes lose information about leakages between ports, and that makes a bit messier schematic. But that's life. And in some cases, we have to define which elements should be modeled together and which can be modeled separately. The probability of leak comes from good practice. There's no clear answer, but wherever ground fields are a bit weak, this is something we need to be a bit more careful with, thinking that we can just run this EM alone without its friends, let's say, around him. One thing that is typical is that the designer finishes a PA, like this one in the bottom here. Everything is completely modeled, and the designer is satisfied, and you see these kind of stability circles in all the differential and single-ended combinations around the PA. Everything's clean. But then you're looking again into a very dense area. This PA won't sit by itself with a lot of ground around him and connect to a clean supply. But this PA will sit in a dense layout with a lot of PA friends from the bottom and from the top. And practically the ground will come from somewhere. And he cannot, this designer, when he wants to generate a design that is a copy and paste and can be used in different locations in the silicon, cannot be sure what would be the ground impedance or ground inductance in his scenario. And a good practice is to take your design and before finishing it, take the full EM model and kind of float all the ground on inductance, which is varying by, I don't know, some 1 to 10 nanohenry, to put into your probability kind of risk assessment, what will happen if the ground is a bit degraded and coming from worse locations. Of course, you can always try in the layout to improve the ground, but eventually it won't be symmetric. And this is something that needs to be taken into account. One thing that I wanted to mention about heat and calibration is that on the left here, you can see, for example, a phase shifter in 2 different temperatures, the blue and the orangish, 2 different temperatures. So this tilt in temperature is an effect of temperature which needs compensation, needs calibration. On the right here, you can see examples of PAs spread around the silicon, while their PTAT, which controls their temperature compensation, is in a cold environment, while some of these PAs are practically handled or working in a hot environment. When something like that happens, you practically don't get what you wanted to get. So either control your heat aggressors or make sure you have a PTAT solution which is closer to the temperature that is practically present in that PA. But you need to understand that when you have a multi-TXs and multi-RXs solution and all controlled by PTAT or CTAT, those control circuits would preferable want to be in the same environmental conditions. Another phenomena which is pretty known is that gradients and the temperature, if they're not symmetrically flowing over modulators, they will create image to rise. You can create kind of, imbalances in the modulator. And again, the aggressor could be situated more symmetrically to those 2 modulator mixers, if possible. And if not possible, faucets for calibration are always good to have with high resolution to calibrate nicely the image in the LO. And this is something that needs to be pre-development for flexibility in the design afterwards. But in general, aggressors of temperature would be better if they have symmetrical kind of effect gradiently on these 2 mixers. Performance verification. So because of the multi channels, having an evaluation board which has connectors to each and every channel, to validate performance is something which is not practical. Why it's not practical? Because millimeter wave connectors tend to change their losses after a few connections and disconnections, and their repeatability and the amount of time takes to connect and disconnect each one from each and every module of a multi-TX or RX module solution is a long time, not so practical. So and if I'm combining that to even cost, so that costs even more. So a better solution would be an on-air that the evaluation board will practically have antennas, and these antennas are well modeled. Once they're well modeled, this is your kind of your safe zone environment, and then you validate performance of each TX and each RX on the air setup. Because of the complexity of the design, which everything is dense together, you quite quickly go to a full module validation with a corner reflector inside the chamber of anechoic chamber to check how the multi-antennas react with the radome and how your antennas field of view and the ERP, and create SNR locations of the corner reflector. Then this product goes to the field, and then you put it on the motorcycle and try to understand if your application works as expected. One more thing that may need to be considered, and even a must be considered, is how would your RFIC perform within, I don't know, 10 years, not only today. And analyzing that, putting aside HTOL tests and other tests that are done in kind of an ACQ process. In the lab, figuring this out and stressing the multi kind of silicon solution, using a controlled software and stressing with the operational software, and having real RF tests like noise figure, like output power, current consumption, and seeing when is your tilting point, when is your devices starting to age, are they starting to age, and what is the performance after aging, and do you have compensating on that degradation of performance after X amount of years, sort of speaking, when you're having these accelerating cases. This is part of a paper that was supposed to be presented in Comcast, will be presented in the coming summer, which a bit gives insight on a multi-device aging characteristic. So you saw a video like this from Ophir, but the end result would be, seeing that the application practically works, that the motorcycle is riding, and then it detects this, this is a cross motorcycle that we want to see that doesn't get into our back. Sorry. So summarizing, hope it wasn't too short, Vadim, but maybe it's good because of our time. We think that motorcycles should be safer, and we want it to be on low-cost motorcycles as well. We see the high channel count and single chip solution as the main direction for that. And we have a lot of thoughts about development progresses that needs to be done towards these applications. Thank you. Questions?
All right. Yeah, thank you so much. Thank you for making it on time. We are a little bit, let's say, exceeding the time. Maybe we can take one short question, and then the rest maybe you'll be able to